Okay, well, thank you very much for the invitation and for this workshop. I'm going to talk about another way to modify gravity with a different motivation, which it has different roles, but that is also, in the end, relevant for many of the things that have been discussed here, so I think it's going to be interesting for you. Since I'm going to focus on the cosmological implications, though I will have to go through a lot of material to arrive to cosmology, I only mentioned the collaborators I work with on these topics. This is a bunch of papers on different aspects of the problem. First thing I want to say, I will discuss only late-time cosmology, because otherwise it's impossible in 45 minutes. And you can imagine that if you break something as fundamental as Lorentz invariance, you may also find implications in early cosmology, and those are very interesting. Some people in the audience here also worried about that. But yeah, you will have to ask me later, or we can have another session. What I want to advertise also is that if you are interested in everything, we wrote a review recently with Jean Lim that you can find. Please, if you have any comments, write to us. We would like to be comprehensive. And the other papers I was mentioning here had to do with implications for dark matter, implications for dark energy, what you learn about the gravity, from this, about Lorentz invariance in gravity from the CMB and landscape structure. And also, maybe for this audience, massive gravity would be more interesting, but since next week Sergei Sibiriakov will be here and he will give a full talk about this, I will just very briefly comment what we can say about massive gravity if you violate Lorentz invariance. Okay, so let's start with a kind of philosophical transparency slide with the gravitational theories landscape. Okay, so I think it's nice to understand where we are in the full landscape of gravitational theories and what we want to do and in which directions we can go. So if we want a minimal unitary Lorentz invariant massless metric theory of gravity, then almost by there are some theorems that tell you that what you are going to find is general relativity, and let me put this as my starting point in the space of theories. Then, for each of these theories, you have to go to the roads of the phenomenology, and some of these roads are nice and warm. Some of them are very hot, so whatever happens there is going to be so hot that maybe you can car. So, what we want to do, we modify gravity, is to move in one direction in which you somehow find a valley of opportunity that allows you to flow easily in this phenomenological direction. This is, and in particular, you want two particular points to be, let's say, less hot than in GR. One is everything that has to do with quantum gravity, and also objects with very high densities, like black holes. And of course, the other interesting thing would be if you manage to get a dark sector with better properties than in GR. And in between, you have all the different plethora of experiments and observations that you must, well, it may happen that if you move in one direction, you are easily flowing at some scale, but then you find that, I don't know, maybe for the solar system, you are back to a complicated situation. So Lorentz evaluation allows you to somehow have a valley that is always nice, though it has its own problems that I will discuss. Okay, as I say, in this journey, what you want to do by exploring this, well, for instance, I want to emphasize that it's not, I mean, of course you can take points in between. You can say, well, what happens if I break Lorentz invariance and I have massive gravity, for instance? And I think that all of this is very nice, but the first motivation shouldn't be, I do this because I can, but yes, it should be, I want to learn something about gravity fundamentals, so I ask very well posed questions. and I move in this direction. It's not that I just put a potential, crazy potential, and let's start with it. No, it's like, is the graviton massive? Yes or no? Is the graviton massive Lorentz invariant? Yes or no? These kind of things. At least I already mentioned. And finally, yeah, of course, you want something that you can test. So that's my landscape, and yeah, no more on Blas. So as I said, Lorentz, in a sense, Lorentz violation is like kind of a valley in the landscape, as I will explain. But then, why do we insist so much in it? Okay, why do we make it a key ingredient of particle physics, gravity, and the dark sector? Well, there are two different possible questions you want to ask about why do we do this. First, is it necessary? So is it the case that we do this because that's the only possibility? Also, is it we do it because there are super stringent bounds and are telling us something about nature? And the second is what happens for the particle physics, where I will tell you what is this number, but it is a dimensionless quantity that gives you information about deviations from Lorentz invariance, and you see that it's very tiny. So this could be order 1. I will tell you what it is later, but let's say that that's a kind of typical dimensionless quantity that you find if you violate Lorentz invariance in the particle sector. Could be 1, is this number. And in gravity, those bounds are much minor. So yeah, in gravity, then you can start asking the question: is it really necessary? Okay. And what do we win if we break it? I want to say that all these bounds are natural in the sense that since they are related to a symmetry that you are breaking, whatever number you find is technically natural. So it's not. It's not that because it's very small, you should be worried about fine-tuning. What is fine-tuning is that for instance, you have this in the standard model. Then why do you have this other number in gravity? This requires some extra thinking, but the fact that you have a small number is not a problem. Okay, so given that number, yeah, why do I say that this is a kind of ballet for gravity? Well, first, something I'm not going to talk about because the talk after me will be more related to quantum gravity, is that there is, in this very hot plate, which is quantum gravity, here we are in a much nicer situation than in GR, something that Peter or Java put forward in 2009, and also people doing causal dynamical triangulations, they prefer this kind of theories to GR. They are simple to find as infrared theories of gravity, of quantum gravity. You also have in the air new ideas about black holes. I say in the air because we are still working on them. At large distances, there is a natural way to provide acceleration with a very simple potential. And finally, well, not finally, but just to make this list finite, recently we realized that there is a Higgs mechanism for massive gravity within this approach. Okay? Are we good? Now, how do we want to break Lorentz invariance? You don't want to be completely agnostic about Lorentz invariance, about symmetries. Well, you can do it. This is a possibility. You want to say. You can say, well, we're going to try to study the most possible theory in the universe. Okay, good luck. I think it's. Let's say I want to be minimal in the sense I want to be minimal. In the following sense, that I will try to introduce the minimal number of elements that allow me to get better UV behavior than in GR. And this you can do just by assuming that in the universe there is a preferred time direction. Okay? It's not a preferred time, it's a preferred time direction. So in the universe there is a space direction, a time direction, and in each point of space-time you have a kind of preferred vector which is time length. And once you want to impose this kind of thing, about 4 vector, you face two possibilities. One of them is that this 4 vector is completely generic. Only thing is that it is fixed norm 1. Okay. Then this theory will have 3 extra degrees of freedom here with respect to GR, But you can also, and it's called Einstein ether, you can also say, well, I don't need all this. I can just say that there is a preferred scalar field with an expectation value that is time dependent, and that defines for me this time. Okay, this is what we call chronometric theories from time, and because you have a kind of preferred time and a metric in the game. And yeah, as I said, I mean, this frame is relatively simple to understand. There is this preferred foliation, let's say, correspond to preferred values of the field. For people who care about extending theories and scalar tensor theories and scalar vector tensor or whatever, you can understand these theories are scalar tensor, but where the scalar has an extra symmetry. Okay, it's a fully reparametrization invariant symmetry. So you are used maybe to symmetries of phi going to phi plus constant, okay, or phi, I mean, making rotations in internal space. This is a kind of sigma model for the field. Okay, that tells you that since I want this theory to be reparametrization invariant and the time reparametrization in this framework, in this language, that means that I have to allow my field to be reparametrized. Okay. So this defines for you a class of scalar field theories. And the consequence is that the way this scalar enters into the Lagrangian is not through derivatives. For instance, you cannot just take a standard derivative of phi because it's not invariant under this symmetry, but it has to come in the Lagrangian through this combination, so through this unit vector field. But besides that, you can completely forget about this picture and say, I want to study this class of theories. So when people say, this is the most generic scalar tensor theory, you have to consider that you may be also having these possibilities. Okay, so good. Now, once we have these two ingredients, like the metric and this preferred time direction, you can proceed as you normally do in the same effective description. Like I have my field content, I have my symmetries, which in this case are going to be, well, this is a reparametrization of phi in this case, full diffeomorphism. I didn't say it, but I have, going from this picture to this picture, what I'm doing is I am Stuckelbergizing my theory, so I am somehow thinking that this breaking of Lorentz invariance is due to the presence of this field, right? So I can always go to the, let's say, covariant gauge, or sorry, covariant language, and then just play with phi and the metric, and then build the most generic action as a starting point. This action is going to be a standard general relativity Einstein Hilbert, and then a bunch of possible derivatives you can start playing, putting over this field. Okay? And low energies, that's what you can get for this chronometric theory. See, there are only 3 new terms. In principle, this is going to be also, I put this here because this is the infinite. There will be also other operators that with more derivatives that will be suppressed by a certain scale. But for the moment, let me just focus on these three operators. And immediately, you can, from this Lagrangian, deduce that the theory is a theory with a massless spin to graviton. This graviton is massless, but still the dispersion relation is modified by this quantity, one of these quantities, but that, by the way, corresponds to shear, which is something that, in principle, was understood this year, that whenever you have shear in your theory, the speed of propagation of gravitons is modified. It should be. And also there is an extra scalar. There is the way to parameterize it, that you say that this phi is going to be has a background that you can define as your time, and then some fluctuation over this background. And this fluctuation has a dispersion relation, which is the standard one, with a certain speed. Right? That was for the chronometric, where you have a scalar tensor. Einstein ether add an extra possibility. There is an extra term you can write. That in the case of when you can write the vector field in this way, you can reabsorb this term combinations of these other coefficients. If you have a completely generic case, that's not possible. So there's an extra term in Einstein ether. And extra polarizations, which are vector fields. An extra spin-1 polarization. And those are also massless. Okay, so that's the infrared, let's say, like the infrared. This theory is a nice effective field theory. And the cutoff of the theory is relatively easy to understand what it's going to be. You see, because this is an interacting quantum field theory, and the role played by M. Planck in the Einstein-Hilbert action here is being played by M. Planck square root of this parameter, right? Because that's, if you want, the scale in front of these operators. And this is precisely what? A combination, let's say the smallest of the possible combinations is going to be the cutoff of your theory. And you see that, as you all suspect, you cannot put this to zero. So this number shouldn't be too small if you want your theory to make sense. I mean, at phenomenological distances. So if alpha were, or beta or lambda were 10 to the minus 60, then this theory would have a cutoff way above way below, sorry, the scales at which GR works. So it couldn't be trusted, at least as an effective theory. Another nice feature of this is that, as I said, there is a possible way to complete the chronometric case. So there is you want a selection of operators you can make that provides for you a power counting normalizable theory. And that's, as I said, I think that Emil will discuss this afterwards. For the Einstein ether theory, I think there have been some attempts but never published, by different people to try to see if can be completed. Not clear yet. Now, that's one of the possibilities you have for the infrared. That's the minimal one possibility. There is just one preferred time direction, and the graviton is massless. Now you can say, well, how do I do a massive gravity in this case, that I have a preferred frame? Now the ingredients, you need something else. Okay, so you have this chronon field in town. By the way, we only know how to do this for the chronometric case, not for the Einstein ether. And you have the metric, and then you want to break. So this broke the once you select the unitary case, when this is the time, this breaks diffeomorphisms to the diffeomorphisms that preserve the foliation. Let me go back. So the fact of having this preferred time direction still preserves the fact that you have all the diffeomorphisms in each of the time slices, and also as I said, those that reparameterize your time. To do massive gravity, you want to break this further to have only Lorentz invariant or SO3, but not local diffeomorphisms. In this case of Lorentz breaking, for instance, you can allow yourself to break local translations to those translations that depend, those are local also, but with a particular functional dependent of this field, which is, as I say, you can understand this as time. If you do this, you realize that the only massive terms you can have are these two. Okay, and this gives this in particular, this gives mass to the spin to elusivity. So this theory has this symmetry breaking pattern, if you want, has a massive spin to graviton in the spectrum with this mass. Quite interestingly, and this wasn't understood before, this extra degree of freedom that is massless, the chronon in the let's say minimal setup, is also massive in this case. It acquires a mass proportional to the spin to gravity. So in this theory, everyone is massive. The nice features about this with respect to all these complications that you have in invariant cases is that there is no DTV discontinuity, there is no Weissman mechanism involved where there's everything is much similar to what happens in general relativity. And this allows you to complete or to find a way to have a well-defined theory of massive gravity with a very simple potential, for instance. already introducing 3 extra degrees of freedom, or fields, phi I, with this kind of potential to this. So I have this for the chronon, and then I add this simple potential. Okay. Then, by the way, this is a potential which is protected by a symmetry, so it's what it is. At the let's say, it's not normalized. I mean, it's a normalizable potential, at least without the gravity problem. Let's say that we can put it aside. And it has a vacuum for this field, which is of this form. So basically, each field breaks the internal symmetry to a diagonal symmetry, and it generates this mass term for the spin to gravity. I'm not going to discuss this a lot because otherwise this takes the whole lecture. I want to say that this is a nice mechanism. Still, it doesn't really work so easily. Why? Because if you then try to understand what does this guy with this background do for cosmological solutions, you realize that Minkowski is not a good background, and the backgrounds that you find typically make this mass go to 0. So this is a massive gravity where you want the vacuum doesn't have massive gravity. So that's why we needed a more complicated setup to include non-decaying masses. If you want more details, either next week or later, but not now, while you go to this paper. It's relatively, this is very nice. That's really beautiful because it's very minimal. If you want something more like physical, like with the masses that don't have this feature, then you have to start adding, let's say, ugly in the sense that more fields with very particular representations, something like not so nice. Something which is nice about this, and that's basically the summary of what we know about this theory, because we want to do many things that we have not done yet, is that this theory has stable Freeman-Robertson-Walker solutions in the non-accelerated branch. There is also an accelerated branch with Taylor's instability, so we discard it, but maybe something can be done with that. In this case, and this is very nice, there is also a repulsive gravitational potential on that scale. And that's, if you draw the potential for the gravitational field, that's what you find. This would be the standard Newtonian potential. And here you realize that in this case there is a scale which has to do with the mass of the graviton at which it stop growing, and then generate this repulsive potential. Of course, this tells you that this mass shouldn't be inside the solar system, but it may be interesting. Now we want to understand whether you can use this to create an acceleration or something. The background doesn't have acceleration, that's for sure. So at the level of homogeneous isotropy solutions, there is no stable backgrounds that accelerate. But now the question is, can you use this to use inhomogeneities to accelerate themselves at very large distances? Who knows?
When you say accelerate, do you mean accelerate or
repulse?
even if you
Repulse.
Okay. So even if you put a pair of
If I put two particles up here, sure, there is anti-gravity, and this is stable. These are the typical the kind of things that you may find when you don't have Lorentz invariance. That some things that are impossible, like repulsive gravity, here become possible. Now, all this is very nice, and now why don't everyone work on this? Okay. Because of the 10 to the minus 20. Of course, Lorentz invariant is a symmetry of nature at low energies in the particle set. So, a way to do it is that you have the ingredients, as I said before, and now you add. I'm going to now focus on the massless case, so no massive gravity. But I'm going to add standard model fields, I'm going to add dark matter, I'm going to add dark energy. And for each of these sectors, let me separate them into Lorentz invariant case, hard, and Lorentz violation for standard model, dark matter, and dark energy. Now, for what do you do when you have this kind of couplings, here, of Lorentz vibration in the standard model. You can have operators which couple a fermion with this new preferred direction, okay? Yeah, as I said, you can imagine that this direction is like time. So this is going to generate for you a gamma 0, delta 0 term with a coefficient which is arbitrary in principle. It's not fixed by anything. So this is going to change the propagation of the dispersion relation of this fermion. We're going to add a parameter in here. Now, if you then say, well, let me try to understand how well we can test that. There is this guy Kosteleski, whose life has been to help us in this direction, because he and his collaborators have tables and tables of this kind of operators. They have numbers as crazy as this one, like the maximum speed of propagation of protons with respect to photons is different from 1 at 10 to the minus 20. Okay, so clearly the standard model has something that makes it Lorentz invariant at low energy. And in principle, you expect that if this is the degree of Lorentz invariant in nature, it should also be there in gravity, though this may be model dependent. So why to bother about breaking? Well, there are 3 ways to answer this. One way, well, I can always fine tune. I can always imagine that my gravity sector lives in a fine tune. I can say that, well, look, we are used in physics to emergent symmetry. So some fundamental, some symmetries that we think are fundamental, sometimes they are not fundamental. They are just the result of, I don't know, for instance, your theory being explored at very large distances, or just because it's an accidental symmetry, as happens for baryon conservation, for instance, in grand unified theories. So that's what I mentioned here about dynamical explanation. So we are trying to look for, and there are some options to look for, ways of generating these tiny numbers, even if nature is not invariant under boost, in this case, at the fundamental level. 2 examples are RG flows. For instance, the normalization group flows typically tend to flow in the infrared to fixed points which are Lorentz invariant. Typically, if you have a theory in the UV which is not Lorentz invariant, what you are going to find when you are very far away from the microscopic scale is a Lorentz invariant theory. Of course, this running for these parameters is logarithmic, so to generate 10 to the minus 20, even if they tend to be the same when you flow, to generate this number you have to flow for too many decades. That's not good, so we are trying to look for other ways to generate this number with a strong coupling, but this is an ERC project, so we'll see. Other ways are just, there is an observation which is very, very interesting, that if you have supersymmetry and Lorentz, in theories which violate Lorentz invariance, this number is directly 1, just by construction. You cannot play with supersymmetry in a way that you can generate 1 here. And then Lorentz breaking appears with extra derivatives, but then the constraints are not so crazy. So you may have this. The problem is that how do you supersymmetrize chronometric theories? That's also an open question. So the rest of my talk that I'm going to assume is that this is, I'm going to put the number that I learned from phenomenology, so that everything that I can do in the standard model is going to be very small, so I just ignore this, or put it to 0 and try to understand the other numbers, and also the numbers for alpha, beta, and lambda. Okay. So which are the constraints I can put? Well, the first, this theory, I want it to be, now I'm going to be focusing always in the infrared, right? At large distances in this effective stable and no ghost is something that you can easily do by just adjusting some parameters of the theory. Also, as Shinji was mentioning, you want to avoid gravitational Cherenkov radiation, so by putting these 2 bounds. So those are what I call theoretical bounds, but then you can start to also try to study how gravitation really works in this framework. And there are certain number of differences. For instance, here, already for a post-Newtonian, for a system that you can describe with post-Newtonian gravity, things are going to be different because, in principle, when you have two sources or a binary system in GR, if you boost it, nothing changes, right? Because of the invariance and the boost. In this case, if you have a preferred frame, a preferred direction, and you are moving with respect to it, precisely because you are not invariant under this change of coordinates, you are going to be sensitive to this boost. Okay? And it's something you can see just computing the gravitational potential of the sun, for instance, a sun that is moving with respect to this preferred frame, and it will be given by the standard Newtonian potential plus then some factors that depend on this velocity. Okay. In general relativity are zero. So these numbers, which are parameterized by two numbers alpha 1 and alpha 2 in the post-Newtonian parameterization, are proportional to the Lorentz breaking theory. Sorry, Lorentz breaking parameters in my theory. Okay. So something else that happens is that the Newton's constant is also sensitive to this parameter alpha, and this alpha is the acceleration of your system, well, of this congruence with respect to, well, the acceleration of the congruence, let me call it. Now, of course, if you want to then go from these parameters to something that, like some constraints, okay, how big they are, how small they are, you must tell me what is this velocity. And in principle, you don't know, right? Because you have never detected a preferred frame in the universe. So what we are going to assume is that this frame is the CMB frame. So in the universe, there is a preferred frame, which is the repeating frame, right? And then the CMB frame. We are going to align our preferred time with this preferred time that exists in the universe. Why? Well, this is something that we should answer, not in this talk, but something that we should then answer the question why inflationary cosmology tends to produce a frame that is aligned with this vector. We know the answer partially. We know that if you have two vectors in the primordial universe, they tend to align with time evolution. So it is a natural thing to do, to align them. Now, what happens if they are not exactly aligned? This is an open question, which needs to be explored. Okay, so also something that changes a lot in these theories is the gravitational radiation. Here I put, for instance, the bound that you get from binary and single pulsars in the parameters of Lorentz violation, lambda beta, as compared with the solar system. So in the solar system, basically constrains some of these parameters, but not all of them, because if you put alpha equal to 2 beta, that's all you need. So if you put alpha to 2 beta, beta and lambda are completely unconstrained. Now the way to constrain those parameters is, okay, let me see what happens when I have a system of two bodies and they emit gravity waves. Then you go from a almost unconstrained parameter space. These are the constraints coming from stability, so almost no constraint, to this very tiny, you don't even see it. So those are the constraints coming from binary pulsars. Why those constraints are so tight? Okay, and the reason is that, and this is I think is a reason for most of the modified theories of modified gravity. That in principle, if you have a theory that modifies gravity, in the sense that gravitons don't follow geodesics, okay, then if you think about sources moving around, they are not going to follow the Newtonian orbits because there is an extra force. Okay? Already, even if matter is not coupled to your extra degrees of freedom, and if you don't have a Einstein mechanism, okay, then these two sources are going to interchange not only gravitons but also the extra field, which means that as time evolves, this quantity here, the standard momentum, is not going to be conserved, because the momentum that is conserved, and I mean this is basically mxi, you take the derivative, this mv, and normally in Newtonian gravity, this is conserved because the force is what it is. If you change this force, this is no longer conserved. You see what I mean? Orbits are not exactly.
Even at the linear level? Probably.
At the linear level, if you couple it directly.
Okay.
And if it is directly coupled, yes. But normally what happens is that since it is not directly coupled, you need your source to be very compact.
Exactly. So you need the nonlinear effects, right?
Nonlinear effects because you need a kind of core of gravitons in this
the
object.
background is to back react to to modify the edge of the.
But that's kind of, if your object is compact enough, it's going to be there. So let's say that the gravitons interact through gravitons plus an extra field, which is not a screen or anything, then this quantity is not conserved. But this quantity appears when you compute the gravitational wave from sources. Is the famous dipole, and it is enhanced with respect to the quadrupole by V over C factor, by C over V factor.
What about the monopole? I would expect that also, you know,
No, because the monopole
would be there.
The monopole is conserved in these theories.
Ah, okay. Just an accident. Is it?
No, it has
is
to do with
spatial
energy conservation. Energy
Okay,
conservation.
so the momentum is not conserved anymore.
Yeah. This momentum is not conserved. There is
But the
another momentum
energy
which is
it
conserved.
is. But the
You have to
energy.
define it properly, the moment. But the energy is the same. In this theory, you can maybe be more generous.
Yeah.
If the monopole wouldn't be conserved, then this
Even more,
state would be even more.
Did you take the relativistic corrections into account for the monopole? That's what we had as well.
For this, the relativistic of what? So
The higher velocity corrections into account.
these ones, you mean? Or?
For the, yeah.
Yeah, we did everything.
Okay.
We did the, well, not everything. we went to the level that we had some realistic sources and we expand them in some momenta, and we cut them when we at the level that we understood the weather approximations. So for the sources we have, we are consistent. Maybe for other sources, other corrections should be taken into
Yeah,
account.
I guess for the
no.
I mean, for the binary pulsar test, you don't need UT, but at least for correction, right? The quadrupole
No.
is
we took a slow pulse.
yeah. Maybe in the
Slow
future.
systems.
Maybe in the future.
Not very fast systems. Also, we couldn't use Hals-Taylor for technical reasons, but there are now different white dwarf and neutron star systems that you can use. I can explain you later. Okay, now finally cosmology. Now in late time cosmology. What you want to do is to understand this Lagrangian, the gravity Lagrangian. There is this matter, dark matter, and dark energy Lagrangian. Oh, I'm tired. The first thing I want to say is that, as I advertised, there is a very nice model for dark energy. And I say it's nice because it's a simple potential, and it is naturally, I mean, the source of acceleration, it's naturally small or big or whatever you want to put. And we call this theta CDM. Of course, we don't solve the all cosmological constant problem. We just put the cosmological constant to zero, I mean the vacuum energy to zero for other reasons. But then it's enough to add to this framework an extra field with this shift symmetry. Typically, in a Lorentz invariant theory, that's the only thing you can write in terms of normalizable operators. If you add the U in the game, you also have this possible operator, and it's a square. The nice thing is that this mass is a mass scale that can be easily protected from quantum corrections by assuming that all the UV completion is going to be invariant under this symmetry. Since this is not invariant under this symmetry, it cannot be corrected from any UV degrees of freedom. So whatever you have here is what it is, right? So it's UV insensitive, protected by this very simple symmetry. And the effect on the Friedmann equation is exactly that of a cosmological constant. Then of course there are perturbations over it, and we had studied them, and everything works very well. As a dark energy model, of course, we don't solve the. Yes.
Isn't it a bit strange to have an odd operator for theta at low energy and no other operator at high
Well,
energy?
it's called an accidental. This is what it is. I mean, this is
By hand.
it's by hand, of course. It's something that, of course, if you try to understand this from a purely UV point of view, it will be very strange. But let's say that if you have it at the beginning in your theory, you could say the same from any. No, that's what I would say. But yeah, dark energy. Somehow that's the best we could do. That's already something. Let's just focus in the last 5 minutes on dark matter and purely gravitational effects. As I said, well, here there are two possible sources of modifications. One is that this vector field has a background, so if you move with respect to this background, you are hitting it, and this changes your mass. It's like a kind of well, not exactly like the Higgs mechanism, but there is a background that gives you some, let's say it's really a mass. And there are also perturbations of this new field that those are going to mediate interactions. This is what I said about the background, and also the background, by the way, changes Friedman equation. That instead of here being G Newton as before, the Newton that you get in binary systems, here there is a different constant. This is what I said. So given this, you expect that gravitons, because they interact with this field, through these operators, and dark matter, because in principle you can be agnostic about what dark matter does, they will gravitate in a different way, and in principle you don't expect the equivalence principle to be in the game because you have an extra force. Now, if I forget about dark matter, purely gravity sector, okay? Lorentz violation dark matter. Lorentz violating dark matter. So I have the standard matter sector with a Lorentz violating gravity. What happens are two different, the different phenomena are two. One is that the Poisson equation is modified to something that is different from lambda CDM because of a constant in this Poisson equation. So once you plug this back into the growth, to understand the growth of perturbations, then you understand that the way in which perturbations grow is modified by the difference between G Newton and G cosmological. And this is completely generic also. It's not. That's a way if you have a theory of gravity that generates a different Newton's constant locally than globally. This is what you're going to find out. The growth of structure is enhanced or decreased.
Sorry, so basically you're saying that the scale is independent, scale and time independent basically, it's a constant change.
It's constant. In this theory, it's constant. Sometimes people like to parameterize this as a function of time. In this case, it's constant. That's why we get this fact allows us to get better constraints than other people who get parameterized.
And how big is it typically, this enhancement?
Typically, it depends on the parameters. This is what it is. It is order 1 in the difference with respect to 1. That what you want to know, or the power spectrum?
No, basically the enhancement is delta. I just want to know
I will show you the power spectrum. Another thing that happens, as I was saying before, is that these theories have one fluid, which is your dark matter, and another fluid, somehow, which is your preferred direction. Which means that you have two fluids moving with respect to each other in the universe. That means that the energy momentum tensor has some stress. Some non-diagonal components, so not everything flows within the same direction. And this is proportional in this case to one of these parameters. If you add now the Lorentz violation for the field force, what happens is that then you are sensitive to the couplings of the field force to this guy, u mu. And this is parameterized by this Lagrangian, which is the standard Lagrangian for Newtonian gravity, plus then there is an extra term which couples the density of dark matter to this U field, okay? In a way that also, if this is very big, so if you start to have a lot of, to look at the scale where this is very big, this is going to tend to be zero. So there is a kind of alignment phenomenon that I'm not going to explain because I'm running out of time, but there is a nice screening mechanism with different scales in the game. So let's say that it's a field force with a nice feature that I can explain. Now for the power spectrum, as I said, let me just show the different power spectra. So this is the density power spectra of dark matter in models that have, for instance, this is the amount of Lorentz violation in the dark matter. I define here. So this is the new operator in the dark matter. And some Lorentz violation in the gravity sector. If you see that just by eye, this is lambda CDM, just by eye, you are able to distinguish at order 10 to the minus 2 for all these cases. So that's what you expect to, in the end, typically the kind of bound that you expect are at this order. And all this comes from the difference in the load factor. Now for the, zero. Of course, the other scenario you want to look at is the cosmic microwave background, where also you can understand that by modifying, for instance, in the production of the BAOs, for instance, there is, you have the plasma equations, and then there is something that depends on the gravitational potential. But now if the gravitational potential depend on delta with a different constant, this is going to hit back here and modify the speed of these BAOs. And this means that the BAOs are going to be at different scales, okay, typically they are going to move. And also this generates a boost. Typically this piece also gives you the scale that normalizes where the BAO happens. So they say that this number is going to modify the BAO peaks and also their amplitude. Shear, what it typically does, remember that there were two effects, this and this. Shear typically tends to dissipate energy to smaller scales. And yeah, this is what we showed in these two plots in this paper. So this is the lambda CDM, enhanced gravity, which is the equation when G Newton and G cosmological are different. You see that's moved to the right, and there is a kind of different normalization. When you have shear, the only thing you do is you suppress all the scales. Well, here are the bounds, very good. As I said, the bounds on the different parameters are order 10 to the minus 2. Now, is that all? No, by no means. That's all. Okay, I think that we are now satisfied at the phenomenological level, in the sense that we did everything we could. Beyond that, we have to start talking about nonlinear scales, and this is going to be difficult. So we are trying to understand nonlinear structure formation and see what's going to happen. Other open questions are in the primordial universe, as I say, why the alignment with quantum gravity effects, Lorentz violation and inflation, or also maybe some alternatives as bounds. All this is kind of related. As I told you before, even though we don't discuss this in detail because there are many open questions, you can find a review of them in this paper. That's my conclusion. I stop here. Thank you.